Okay, in this video we'll talk about signed numbers and how we represent them. So far we've worked a lot with unsigned numbers, building a variety of combinational circuits and arithmetic circuits like ripple carry adders. And we know that if we have n bits, if those n bits represent an unsigned binary number, I can represent the numbers in decimal from 0 to 2 to the n minus 1. But if I want to represent negative numbers or signed numbers, I'm going to have to encode those numbers a different way. And there are different ways to do this. One way is called sign magnitude representation, which just uses an extra bit to represent whether the number is positive or negative. So if that leftmost bit is a 0, I have a positive number, and if it's a 1, then I know that I have a negative number. So assume I have 6 bits in my sign magnitude representation. As in an example, I want to represent the number 13, positive 13 in decimal. So the least 5 significant bits are going to represent the magnitude. So 13 is in binary 1101, but I have 5 bits on magnitude, so I'll pad it with a 0 on the front. And it's a positive 13, so that most significant bit, the leftmost bit, is also a 0. If I have negative 13, the magnitude will be the same, but my sign bit will be a 1. So with a 6-bit sign magnitude number, what's the largest number and the smallest number I could represent? Well, the largest number is 0 followed by 5 ones, which is positive 31. And the smallest is all 1, which would be negative 31. Okay, so sign magnitude is an easy representation. And for some applications, we may want to use this, but there are 2 big disadvantages. So number 1, it's hard to do arithmetic. If you think about it, addition would actually be kind of hard because I have to check if it's positive or negative numbers. And this is really the big disadvantage for sign magnitude. The other disadvantage is that there are 2 representations of 0, so I'm wasting one of my representations. There's no such thing as a positive and negative 0, there's just 0. So this motivates another very common way to represent signed numbers, which we call 2's complement, or in the textbook we also call this radix complement, or RC. So to see the idea behind 2's complement, let's list out all the combinations for 4 bits, counting up from 0 on this circle, going from 0 counterclockwise all the way up to 1111, which an unsigned binary number would be 15. Now with signed magnitude, the corresponding decimal numbers would be like this. But with 2's complement, I have, for my positive numbers, the same as the sign magnitude, but now for the negative numbers, I've reversed the order. So 100 corresponds to negative 8, increasing until I get to negative 1. So we see that 2's complement obviously gets rid of the negative 0, so now we could represent negative 8, which we couldn't do with sign magnitude. But also, and more importantly, addition is easy. If I want to add, say, 1 and negative 1, I should get 0, and I see if I just add these numbers, treating them like they're unsigned binary numbers, I'm actually going to get 0, the correct result. The same thing if I add 3 and negative 2, I see that also I'm going to get to a result of 1. Another nice thing about this representation, if I want to convert between positive and negative, say I want to go from negative 4 to positive 4, the bits for negative 4 are 1, 1, 0, 0. If I flip all the bits, I get 0, 0, 1, 1, which is positive 3. But then if I add 1, I actually get to 4. Again, let's look at 7. Say I wanted to convert this to positive 7. I wanted to change the sign. I'm going to flip all the bits, so I get 0, 1, 1, 0, which is 6. But then again, I add 1, and I get to 7. So with 2's complement, I can also look at the leftmost most significant bit to tell if it's a negative number or not, similar to sign's magnitude. But when converting between positive and negative numbers, the approach is different, although not that much more complicated. So let's look at how we would do that. Okay, so method 1 for taking a number x and finding negative x, and this is by far the most common technique that you'll probably use, is as we saw above with our circle chart, we'll take the complement of the number and simply add 1. So with this example, we have n equal to 5 bits, and my number is 13. I complement all the bits, add 1, and this is my 2's complement form for negative 13 with 5 bits. If I want to go the other way, I complement all the bits, add 1, and I get back to positive 13. Another method is to compute 2 to the n minus x. So to do subtraction of 2 to the n minus x, so I'm going to have to borrow from the leftmost columns because I have zeros on these initial bits. So I'll borrow 1, borrow another 1, and so forth. 2 minus 1 is 1, 0, 0, 1. Another method is to complement all the bits to the left of the least significant 1, leaving all the other bits unchanged. So for example, if I have positive 5, I'll complement all the bits to the left of the least significant 1, which gives me 1, 1, 0, 1, 1. If I have negative 12, again, I look at the least significant 1 and complement all the bits to the left of that one, so I get 0, 1, 1, 0, 0, which is 12. And then method 4, and this is another common one that you'll likely use a lot, where we treat the 2's complement representation as a weighted code, with the leftmost bit being of weight negative 2 to the n minus 1, or whatever that position is for an n-bit number. It's the negative of that position's weight. So for negative 13, with 5 bits, this represents negative 2 to the 4, or negative 16, plus 3 gives me negative 13. Another example, if I have 1, 0, 0, 0, 1, 0, the most significant bit is equivalent to negative 2 to the 5, or negative 32, plus 2 gives me negative 30. So you can use any of these methods. Personally, the methods that I use most frequently are number 1 and number 4.